All right. Okay. Thanks for coming, everybody. This is Emma Lieb. She's an undergraduate here at CU Boulder, and she's going to be presenting her work in theoretical galactic dynamics. All right. Go ahead.
Hi, everyone. So thank you, Angela, for inviting me to give this seminar today. Thank you all so much for coming. So I'm talking today about leading spiral arms in isolated disk galaxies. This talk is based on a paper that I wrote with Angela and Anne-Marie Madigan. So let's get started. So I'm going to start with a brief outline of my talk. First, I'm going to explain the current picture in the field and give some background. Next, I will discuss spiral density wave theory and bar-driven spiral arms. Then I will showcase our simulation in great detail. Next, I will explain the mechanics of our system that allow for this unique behavior. And finally, I will touch briefly on my current work for this project and end with why you should care. So the most common galaxy in the universe is a grand design spiral galaxy. The direction of winding of the arms of these galaxies will exhibit either trailing or leading sense with respect to the galaxy's rotation. So for this galaxy that I pictured, it rotates clockwise as indicated by the white arrows. And so then these arms trail behind the rotation. A good rule of thumb to tell whether or not these arms are trailing or leading is to look at the tips of the arms, and if they are pointing in the opposite direction of the rotation of the galaxy, then these arms are considered trailing. So indeed, when we look out in the universe, we find that these arms follow a trailing sense much more often than not. As the galaxy rotates in the direction indicated by these white arrows, our arms, more often than not, always trail behind. There are only a few known examples of leading spiral structure in nature. The most famous example is NGC 4622 that I've pictured here. You can see that this galaxy actually hosts two sets of spiral arms. Like I explained before, we can tell these arms are leading because the tips of them point in the same direction as the galaxy's rotation. This inner arm, indicated by the green circle, is an inner trailing arm. So this galaxy, for example, is believed to have its leading arms because it has a tidally interacting gravitational perturber, meaning there's a little galaxy, a smaller galaxy that is orbiting this galaxy in the opposite direction of its rotation, which tidally disrupts this system and allows for our leading spiral arms. So there is a major challenge with determining if a galaxy has leading or trailing arms in nature. So this problem lies in their inclination with respect to the Milky Way. In order to measure a galaxy's rotation, our line of sight needs to be tilted enough on the galaxy that we can measure a Doppler shift on one side versus the other. But to know whether the arms are trailing or leading, we have to observe the galaxy face on enough where we can actually tell that there are arms and which direction the arms are turning. So the current picture in the field is basically, up until now, researchers have been asking the question, are leading spiral arms possible? Are leading spiral arms possible? So as I said, we found a couple examples where, yes, it's possible if we have a retrograde perturber. Up until now, most simulation are not run with a spinning dark matter halo around them. This is where we come in. Our simulation is unique in that we have put a disk in a retrograde rotating halo because it simulates, we hypothesize that it could simulate the same behavior as we see, like for example, in NGC 4622. So now that I've somewhat painted the picture for what spiral arms look like, I'm going to cover how spiral arms even come to happen. So the standard evolution of a spiral galaxy looks like this. Disks start axisymmetric and then sometime later undergo what's called the bar instability, which forms a stellar bar in the center. Bars work to lower the energy of the disk, condensing in the central region and moving angular momentum outward. To do this, they generate spiral arms. As the bar breaks against the outer disk and halo and slows down, these spiral arms carry angular momentum outward and move to larger and larger radii, which you can see here. So these arms, they start pretty close to the bar, and by later times, they're farther from the bar. They move outward as angular momentum moves outward. So this is the standard picture in a non-spinning halo. This is just how bars form and how spiral arms come to be in a bar-driven system. So assuming that spiral arms are density waves rather than material structures, we employ what's called the Wenzel-Kramers-Brillouin-Jeffreys, or WKB approximation. Very, very generally speaking, this is a way that you can approximate solutions to differential equations. For our purposes, however, it states that the potential minima, which correspond to surface density maxima, which are our spiral arms, will be located on loci defined by constant phase. So this phase depends on the inverse of the wave number of our spiral arm. This approximation allows us to use the inverse of that wave number as an accurate measure for the variations between the phase function and the amplitude function in the disk. As a result, density wave theory predicts that trailing and leading waves are possible and cannot be distinguished from each other. So in a bar-driven system, there will always be two components, a leading arm and a trailing arm. Swing amplified spirals get amplified at what is known as the corotation radius, which I indicated here by this black dashed circle. This radius is defined where the pattern speed of the bar, or the rotational speed of the bar, matches the rotational speed of the disk. This resonance is created because galaxies have differential rotation. So as you move to larger radii, the pattern speed of the disk actually decreases. So that's also another way to say that closer to the bar, the stars are actually orbiting faster, and farther from the bar, the stars are actually orbiting slower. So both sets of arms get generated right at the end of the bar. The leading arms will move inward and they get absorbed at this corotation resonance. The trailing arms will move outward and get amplified at the corotation radius. So in our simulation, we have a counter-rotating dark matter halo, which forms a sufficient substructure that breaks against our stellar bar and moves this corotation radius very far out. As you can see from these plots, our corotation radius is indicated by the black circle. So these frames are showing once every 2 complete bar rotations. As I move to the next set, you can see that the increment between these frames is increasing, which tells us that the bar is slowing down at an ever increasing rate as the simulation goes on. By the end of the simulation, the corotation radius has moved completely outside the disk. So here I just provided one more visualization of this corotation resonance. It's indicated by this red dashed line here. And this black line indicates the start of our leading spiral arms. So you can tell once they start, our corotation radius just flies away. And that's why we get to see them for so long. So which arms actually get to thrive? This cartoon is supposed to indicate quadrants in which arms will either be amplified or absorbed. So like quadrant 1 here, quadrant 2, 3, 4. So inside the corotation, according to the WKB approximation, when the wave number of the spiral arm is positive, you will always have trailing arms. And when the wave number of the wave is negative, you will always have leading arms. Long waves are positive. They are reflected and amplified at the resonances by string amplification. And short waves are negative and they get damped at resonances by something called Landau dampening. So therefore, inside corotation, long leading waves get amplified and short leading waves get absorbed. So in quadrant 2, we can see this leading wave inside corotation will be amplified. This short trailing wave will be absorbed inside. Outside corotation, the opposite is true. Long trailing waves will be amplified and short leading waves will be absorbed. That's quadrant 4 here. So the trailing arm in quadrant 4 will get amplified and the leading arm in quadrant 2 will get amplified. Dynamically, I mentioned before, inside this radius, the stars are actually traveling faster than the bar, and outside this radius, the stars are actually traveling slower than the bar. So it correlates that the stars are going to populate the leading wave here and populate the trailing wave here. This also makes complete sense when we look out into the universe and we don't see pretty much any examples of leading arms. This is because corotation is usually very close to the bar. There usually is not sufficient substructure that pushes corotation out. So it makes sense that we only ever see the wave that gets amplified out here. So theoretical works of stellar bar evolution predict that bars will slow as the galaxy evolves, which naturally moves corotation to larger radii. We therefore expect a barred galaxy to always host a leading arm inside corotation, and they connect to trailing arms just beyond it. This was actually supported as early as Toomre 1971. So hopefully I have now explained why leading arms are allowed to happen. Let's actually go through our simulation and see them take shape. So in this study, we simulate a galaxy with a collisionless n-body disk of 10 to the 6th stellar particles with a total disk mass of 10 to the 10th solar masses, and an isotropic dark matter halo consisting of 10 to the 7th dark matter particles for a total halo mass of 10 to the 11th solar masses. Cosmological simulation tells us that a range of halo spins are possible, but until now it's pretty rare to see spinning halos in simulation, or like modeled. This is what makes our simulation unique. Our halo is given a spin of lambda minus 0.1, and the minus is what tells us it's retrograde with respect to the stellar disk spin. Okay, so here's a surface density plot, or the next many plots are going to be surface density plots of our simulation. Trailing arms are clearly present by 4.27 gigayears, shown here in panel A. They begin with a trailing sense for panels B, C, and D. So I'll just indicate them here. We have trailing arms and trailing arms. See, there's an overdensity. The galaxy's rotation is indicated by the black arrow here. So the spirals then appear to warp around our bar, forming a somewhat complete loop until leading spiral arms emerge. These spiral arms are very long-lived. Again, sorry, the galaxy is rotating counterclockwise here, so we can tell this overdensity of particles here is definitely a leading wave. Like I said, these leading arms are long-lived. They exist for almost 3 full gigayears until panel J. Around 9 gigayears, however, the bar undergoes a second buckling instability. This results in the detachment of our leading arms from the ends of the bar. This makes sense because the pattern speed of the wave is actually larger than the bar now. So they sort of appear to reattach at the end, as shown in panel L here. But we ran the simulation longer and we actually found that this is just a transient feature. They just look like they're trailing arms, and no arms are actually being generated by the bar anymore. Okay, So now I'm going to provide some further analysis of our long-lived leading spiral arms. We're going to look at the flow of angular momentum through the system at all radii for all time, and it shows us some really interesting things. So this plot has some lovely and complicated units, but we're going to look at it like this. We'll say a gain of angular momentum is indicated by red, and a loss of angular momentum is indicated by blue. This plot, the x-axis on this plot is time in giga-years, and the y-axis is actually binned radii. So what this plot is showing us is the rate of angular momentum change within each 1 kiloparsec radii at each time step. So, as I explained before, very early on, the bar forms via the bar instability. This is the flow of angular momentum from its creation is indicated by the first sink of angular momentum into the inner halo that I indicated here. This sink is followed immediately by what we would call the buckling instability. The buckling instability is a result of our disk starting axisymmetric and thin. So here's what it looks like. When the bar forms, the thin disk is susceptible to buckling because the radial dispersion increases rapidly at this time. The buckling, which increases Z dispersion, promotes bar growth and results in a thick disk. This process is very well known to happen. So after the buckling instability, this dashed black line indicates the start of our spiral arms, of our leading arms actually. So we see during this time another sink of angular momentum in the inner dark matter halo. So rather than giving angular momentum to the spiral arms and moving them to large radii, like what would happen without a retrograde spinning halo, the bar in the presence of the retrograde rotation instead forms this dark matter wake. As a result, the spiral arms stay within corotation instead of moving out, which creates the perfect environment for long-lived leading spiral arms. So that's this bar. The dark matter bar is created by the counter rotation of our dark matter halo. So the stellar bar here is indicated by the black line. Its rotation is counterclockwise, as indicated by the arrow. So the dark matter bar is rotating, clockwise. The obvious perpendicular structure here is torquing the stellar bar heavily and slowing it down rapidly. So bars are really overdensities of particles on elliptical orbits. We can approximate them as elliptical orbits. So these planar orbits of the dark matter particles are torqued by the strong stellar bar orbits. But since in this case, the dark matter is precessing in the opposite direction of the stellar matter, the acceleration of these orbits is in the opposite direction, causing the dark matter orbits to slow down and pile up aligned perpendicularly to the stellar orbits. This almost perfect perpendicular bar causes the strongest torque that could be produced on the stellar bar, which slows it down significantly and moves corotation very far out. So back to our angular momentum flow. Lastly, we notice a steady increase of angular momentum to the outer disk, which is associated with the second buckling instability. At these late times, the leading arms detach from the bar and wrap around it and seem to attach to the other side, as I explained. In general, it's obvious that angular momentum is staying within the inner parts of this halo disk system, which is what lets us see these long-lived leading spiral arms for long time scales. So now that I have described all the mechanics that allow for our leading spiral arms, let's watch the simulation. This movie is a collection of face-on surface density plots of our galaxy. Trailing arms are clearly present by about 4.3 giga-years. They begin with trailing sense. So let's watch as the leading arms begin to emerge around 5.8. So here you can see them. They're really strong and beautiful. As I said, they exist for a long time, about 3 full giga-years in the simulation. The X and Y axis here are just kiloparsecs. Around 9 gigayears, the bar undergoes the second buckling instability. The weakening of the bar here results in the detachment of our leading arms, and as I described, the pattern speed of the wave is larger than the bar, so that's why they wrap around, and they are really just transient features here. These are not actually trailing spiral arms at the end. Okay, so the major takeaway from this work is that if the bar is slowed significantly enough, it will move co-rotation outwards beyond the disk, allowing for long-lived leading spiral structure. So while we've proven that this is possible with a counter-rotating halo, we hypothesize that any mechanism that torques the bar and slows it down and moves co-rotation out will allow for leading spiral arms. Okay, so now that I've shown you my simulation and explained the mechanics, let's talk about what I'm doing now and where this project is going. So since we've proved that dark matter substructure has significant effects on the kinematics of galaxies, we are continuing this work by asking the question, are dark matter spiral arms possible? And if so, what is their effect on the kinematics of galaxies? So this plot is my first attempt at trying to discover dark matter spiral arms. It is basically the ratio of the surface density of dark matter particles from the 0th time step to the 1st time step. So the black circle here indicates the sun's orbit, sorry. Okay, so we know that stellar spiral arms are places of active star formation, and in their wakes commonly is found dust lanes. So we speculate that there may be observables that we could identify through understanding dark matter spiral arms and their effects on the kinematics. Obviously, this is currently speculation, but it could provide some really exciting insights into galactic habitability. So let's sum up. To reiterate, with this work, we are reopening a once closed question, are leading arms even possible? I explained that in a bar-driven system, density wave spiral arms work to move angular momentum outward. When there is sufficient torquing on the bar, it will slow, moving co-rotation to large radii, resulting in leading spiral structure in the region between the bar and the co-rotation radius. These leading spiral arms act to move angular momentum to the inner halo. This is sufficient evidence that leading arms are in fact possible, which is really exciting. To conclude, any complete picture of spiral arm theory from now on must include the possibility of leading spiral structure. I'm going to leave it there for questions. Thank you so much for giving me this opportunity to share my work.
Great job. That was great. Let me